everyone. Today we are going to continue with our previous lecture on isentropic efficiency, where you have take a look at this video previously where I explained about how are you going to solve the isentropic efficiency problem. And in this video, I'm going to show you with one example on how to solve this isentropic problem. So before we move ahead, I would like you to have a look at your notes over here. Please make sure that you have your notes and also this mind map that I provided you with. And also if you have a textbook, you may have a look at subtopic 712. Alright, so let us recap a bit on what we have learned so far. So by now we are already in open system. Right, we are already in open system and we have 5 common devices over here, and it is intended in this video to show you an example from one of these which make use of either two of type of working fluids. So you will see that if you have vapor, you are going to have two commonly used, which is water and refrigerant, and if you have an ideal gas, we have air is the one that commonly used, and also some of the gases listed in table A2, which is your the one that we are using, your thermodynamics textbook, this one. Okay, before we proceed, okay, I want you to pause this video and read first the questions over here, and also I want you to read the several questions that you need to check upon once you have settled reading the questions. Now that you have read all the questions and also these sections over here, it is important for you to ask and also check on your understanding based on the things that I've listed on the right side of your screen. So you need to identify what is the device used in this problem. So you will quickly notice that you are going to use a turbine, so you can put a check marks on here that you already have identified it. And then what is the type of working fluid used, and you will see that we are going to use a steam, which is this one is actually your water vapor, right? And then next, what are all the given values or the state properties? So if you have a look at here, you were given entering value, which is 3 megapascal and 400 degrees C, and also leaving value, which is 50 kilopascal and 100 degrees C. Okay, and then next, what is the mathematical expression that you are going to use? Alright, so this is where we recall back the notes from our class, okay, which is, since you have a turbine, right, so this is your turbine, we are going to draw this turbine, okay, and the mathematical expressions that we are going to use is this one. But as I mentioned in class, I do not like you to start from here, because some of the problem might have given heat value, right? For this equation, it is an adiabatic equation. So the best part is that make use of this yellow box equation. We are going to make use of this steady flow energy equations, and we are going to cancel out some term that we are not going to use. Once you identify all the things that you need to list out, right? Then next thing is that you need to sketch the device and also write down the mathematical expressions. That I've already sketched the turbine over here, so you can see that the flowing is from up to down, meaning that you have an expansions of pressure. So you will see the pressure drop. P1 is 3 megapascal and your P2 is becoming 50 kilopascal, and it will also affect your temperature drops, which is from 400 to 100 degrees C, right? So next, what you are going to do is you are going to list the steady flow energy equations, and I'm going to show you on how to cancel out unnecessary term. Okay, so let's go back to the questions that we have up here. Okay, so given to you, this is an adiabatic turbine, so that's why you can cancel out the Q term over here. And because you know that this is a turbine, so you are going to have work out over here, right? And that next is that it doesn't give you the potential, the kinetic energy, so this term is also can be cancelled out, right? And it doesn't gives you the potential difference, so this is also can be cancelled out, right? So that's left you with m dot h2 minus h1. Okay, and you were asked to find this isentropic efficiency and also the mass flow rate of the steam. So obviously you are looking for this one, and also for the isentropic efficiency, again, this is where you need to have a look at your textbook. Under the topic 712, what is the mathematical expressions or formula for isentropic efficiency of your turbine? There you go. So you will see that it is actually an actual turbine work divided by isentropic turbine work. So I'm going to copy this down. Right, so if we expand it, right, if we expand this next equation, it's going to be work actual over work isentropic. In this case, this is going to be your H2A minus your H1 over H2S minus your H1 times with 100. So you see you have two different equations over here, and I'm going to rearrange this one at the bottom. I'm going to have two mathematical expressions. One is used to find your m dot, and the other one is used to find your isentropic efficiency. Mathematical expression shown, you are already be able to identify how are you going to find out the thing you were asked. The second part of the video, we will try out together on how to solve this problem.